And what you're going to see is why we even have the substitution rule. But right now I will say the way we know how to evaluate integrals, especially indefinite integrals, because if you have an indefinite integral, no limits of integration, you cannot use your calculator to find this because your answer is a function. Your answer is not just a value. So your calculator can only give you the value of a definite integral. Indefinite integrals you have to know how to find by hand. So you have to be able to find an antiderivative. So we only know antiderivatives of specific types of functions. So if you have a product or a quotient of two functions, we don't have an antiderivative rule for products and quotients like we do for derivatives. This is where the substitution rule is going to come in. So I'm going to show you how to use it in an example and then go through what the formal definition says. And then we'll just go through more examples today of using it. So we're evaluating this integral. Here's how you want to use a substitution rule. In the name, you should expect you're making a substitution of some sort. This is also called using u substitution. They use the variable u. So what I'm going to do in this integral is I'm going to rewrite it. I want to change all of the variables, or rather everything that's in terms of x right now, I'm going to change into a different variable u. So I'm going to have everything with respect to u. So I'm going to let u equal, and you'll learn how to figure out what to let u equal, but I'm going to let u equal the quantity that's in the square root, so 1 plus x squared. And then this is called a differential if I find du, and we don't need differentials for anything else at this point. So I'm going to tell you what du is, but then explain it so you understand why it is what it is. So du is equal to the derivative of u. So if I took the derivative of 1 plus x squared, that would just be 2x. But then it's 2x dx. So I'm going to explain why. So this is called a differential. So I said for our purposes, I mean really up until now, like the dx in an integral doesn't really mean anything on its own. There are a such thing as differentials. Aside from this instance now, we don't use differentials for anything. But a differential of u is what this is called. And just to explain it to you, if I have, again, u is equal to 1 plus x squared, and I'm going to write this in Leibniz notation. If I said find the derivative of u with respect to x, I would write the derivative of u with respect to x as du over dx. And that derivative is just 2x. So to get the differential, I would just multiply both sides by dx to get the du alone, and that's where the du equals 2x dx comes from. So another reason to think of why the dx is there is we're trying to replace everything in our integral that has an x in it, replace it with something with u. So I would also need to get rid of the dx. So that's why we're talking about the differentials that are there. So what we should see then, this is what we have based on our substitution. So I can replace inside the square root with u, and then the 2x dx is right here in my integral. So if I rearranged this, you wouldn't have to do this, I just want you to be able to see it. I could rearrange this integral to be the integral of the square root of 1 plus x squared with the 2x dx together at the end. So what you're seeing is the 1 plus x squared becomes a u. The square root is still there. The 2x dx is going to get then replaced with du. So now my integral in terms of u is the integral of the square root of u du. And this is nice because if I write the square root of u as u to the 1/2, I can find an antiderivative for that. I couldn't find an antiderivative for this product right here, but I can find an antiderivative for u to the 1/2. So it turns a complicated integral into something simpler that you can actually find an antiderivative for. So I'll just rewrite this integral of u to the 1/2. So what is the antiderivative of u to the 1/2? And once you actually take the antiderivative, your integral symbol's gone. So that would be you have integrated once you've taken the antiderivative. So 2/3 u to the 3/2. It is an indefinite integral. There's no limits of integration, so you have to remember the plus c. No, so the du then it's just there. It's part of the integral. But up here, it's kind of like, yeah, it's kind of like the dx then. And you're using it then to replace some things in your integral. But then from here, if we started with an integral with respect to x, our answer should be with respect to x. So we have to substitute back in what u is actually equal to. So the integral or the antiderivative is really 2/3 times the quantity 1 plus x squared to the 3/2 plus c. Okay, so what I also want to show you then is you can check these, just like you could check any antiderivative. You can check if it's correct by then taking the derivative of your answer and see if you actually get back to the original function that was in your integral. So if I took, this would just be to check, you wouldn't have to do this, but you could. So if I wanted to take the derivative of this, so the derivative with respect to x of 2/3 times the quantity 1 plus x squared to the 3/2 plus c. In order to take the derivative, what rule do I have to use? Chain rule. So yes, I know we have a product here, but the substitution rule for integrals is really like what the chain rule for derivatives is. It's the antiderivative rule for when the chain rule would be used for a derivative. So if I found the derivative of this, I have to use the chain rule. So I would have 3/2 times 2/3, which is just 1. But then I would still have the quantity 1 plus x squared to the 1/2 power times the derivative of the inside, which is 2x. So here's your square root of 1 plus x squared, and here's your 2x that you had in your integral. Okay, so you can check it. It's not required, but to know if you have the right antiderivative, just take the derivative and see if you get back to what you started with. This du? So the du, when you take the antiderivative, this is your expression. The du, just like the dx, it just has to be there. But when you take the antiderivative, you don't do anything with it. We did use it as a differential to make a substitution, but it's not its own separate thing you have to take the antiderivative of. It's just part of the notation. Yes, it's kind of representing what the delta x meant with the Riemann sums, but it's not, when you take an integral, you always have an integral symbol and then du or dx, whatever your variable is. Whatever's in between those symbols, that's the expression you're taking the antiderivative of. So it has to be there, but it's not part of your antiderivative. Okay, so this is how the substitution rule is laid out. And I know looking at this, maybe for some of you it helps make more sense of it. It might be confusing. That's why I wanted to show you that example. We're just going to go through some examples. But you let u equal g of x be a differentiable function whose range is an interval I and f is continuous on I. Then, so if you have an integral where you kind of see you have a composite function, and then somewhere, if you're letting u equal g of x, somewhere also in the integral you see the derivative of what g of x would be. So this really was the outcome, like this was the derivative of f of g of x from, well, it's not the full derivative, I shouldn't say that, so scratch that, I'm not going to continue. Anyway, if you, I just don't want to say something that's going to confuse anybody, but if you kind of look up here, this is your f of g of x, this is your derivative of g of x, so that's kind of what it's showing. So if you replace u with g of x, then you're getting the integral f of u du, because the du would equal the g prime of x dx, that differential. And I have what the idea behind the substitution rule is there, so you're replacing what would be a more complicated integral by a simpler integral that you can actually find the antiderivative of. It might take some guess and check. So I have a hint what you should try to choose for u, and as you do more problems, it becomes more clear what u should actually be, what you should choose. But try to choose u to be some function in the integrand whose differential also occurs. So if you see, oh, I see this expression and I also see its derivative, that would be a good choice for you. Yes. If that's not possible, and this is probably the most common, try choosing u to be a complicated part of the integrand or an inner function of a composite function. So yes, in example 2, one thing that stands out to me is x to the 4th plus 2 is inside of cosine of x. In the example we already did, 1 plus x squared is inside of a square root. So an inside function is a common choice for u. If your first guess for u does not work, try something else. So one, you need to be able to choose a u. You need to be able to see if it's going to work and know whether or not it's going to work. But if it doesn't work, try something else. So it might take some guess and check. And like I said, the more you do, the easier it is to identify if something will work or not. So if we look at example 2, yes, I see I have an inside function for cosine. So that would be my first choice to try for u. I would say I'm going to let u be the quantity x to the 4th plus 2. Because then du will equal what? 4x cubed dx. Now here's what you have to check though. So if you made the substitution and getting rid of the x to the 4th plus 2, that's going to be now cosine of u. And I do have an x cubed dx. I don't have a 4. That's okay. If all you're missing is a constant factor or a coefficient, that's okay. What you have to do, though, is because what I have in the integral is just x cubed dx, I then have to divide each side by 4, meaning this is now going to be, you can either keep it as du over 4 or just write it as 1/4 du. But now when I make a substitution, this integral is going to have a coefficient of 1/4 with it. The 1/4 has to go in there as well. So when I rewrite this, so between the x cubed dx, that is getting replaced with 1/4 du. Okay, now I don't want to skip too many steps and confuse anybody, so please let me know if you're not sure what I'm doing. When you have a number like this with the du, that is really just a coefficient. It can immediately be just put in front of the integral. Because any coefficients can go out in front. And that's usually what I'll do is I'll just put that coefficient in front right away. So I would have 1/4 times the integral of, I am now going to have cosine of u. And the x cubed dx, I already put the 1/4 in there, that's getting replaced with du. So you have to make sure everything with x is now gone, but you're also only replacing what was in there, any other coefficients you include in there. So any questions on using the substitution, just getting to this integral? Okay. So then cosine of u, we know an antiderivative for cosine is what? Sine. Is it sine or negative sine? Antiderivative is just sine, because the derivative of sine is cosine. So The 1/4 coefficient stays. Antiderivative is sine of u. I need a plus c. And then I substitute back in the x to the 4th plus 2 for u. So it's 1/4 sine of x to the 4th plus 2 plus c. Questions on that one? Okay. I included a bunch of examples. I know different things can come up. I just want to give you ideas for how to work through these. So example 3, integral of the square root of 2x plus 1 dx. So keep in mind too, because you'll want to recognize, I mean, now we're in the section with the substitution rule, but moving forward, you want to be able to recognize, do I have to make a substitution or do I already know what the antiderivative is? So like if I give you right now the integral of x squared, you can find an antiderivative for x squared. So you have to determine, do I already know an antiderivative or am I going to have to make a substitution? I mean, today I don't have any tricks on here. We need to do substitutions, but just be thinking of that too. So we don't have an antiderivative for the square root of a quantity. If it was just x, it would be fine. Ideas on what you would choose for u. So, okay, 2x plus 1, what's in the square root? And that means, yep, so du is equal to 2 dx. So then I have to check my integral. The 2x plus 1 becomes a u. I have a dx, but I don't have a 2. Yep, so I have to divide by 2. So 1/2 du is equal to dx. And that 1/2 can be in front of the integral right away. So now this becomes 1/2 times the integral of the square root of u du. And we had this integral before. This is u to the 1/2. So we'd have 1/2 times the antiderivative was 2/3 u to the 3/2. And for the constant, you don't have to include, like with the antiderivative plus c and then multiply c by 1/2, because a constant times 1/2 is still a constant. So you can still just include the plus c at the end. You don't have to have 1/2 c. And you won't see that, I'm thinking like on multiple choice questions for the AP test, you're not going to see 1/2 c's on there. They'll just have c. Lydia? Yes. Yeah. So, yep, here I would simplify and replace the u with 2x plus 1. So we have 1/3 times the quantity 2x plus 1 to the 3/2 plus c. Yeah, they might have this one written as the square root of that quantity cubed. Yes. Example 4. I don't know if you've seen this before. Anyone know what this means? Yes, so this is, it's kind of like with the trig functions. It's another way of writing natural log of x, that quantity to the 4th. So if you had to make a choice for u, I'm hearing some natural log. Oops. Natural log, that is an N, not an H. That's not a great N. Natural log of x. And again, you try it. If it doesn't work, you try something different. So if u is natural log of x, what is du? So derivative is 1 over x dx. Do we have a 1 over x? Yes. So this, another way I could write this, this is the integral of the natural log of x to the 4th power. Since it's over x, it's really multiplied by 1 over x. Okay, so I do have the derivative of natural log in that integral. I do have the 1 over x dx. So that'll get replaced with du. Natural log of x gets replaced with u. I don't have any coefficients I have to worry about in this one. So this is now the integral of u to the 4th power du. And the antiderivative of u to the 4th is what? The antiderivative, I know, the substitution rule, you are doing both operations. You are taking the derivative to get du, and you're doing the antiderivative to get the integral. So just keep track of which way you're going with it. Like at the very beginning of the year. You'd probably be very confused. You wouldn't even know what an integral was. Okay, and then plus or derivative, yeah. Maybe I'll just start with integrals next year. Try it out. Right. Okay, and then I have to replace, so I have 1/5, and then you could write this as the quantity natural log to the 5th, or the way it was kind of written in the problem, you could write it this way, natural log to the 5th of x plus c. If you left it as the quantity natural log to the 5th, that's fine.
Wait, so did you put u into x?
U was natural log of x. This isn't the denominator I was showing, this is u. The x I rewrote as 1 over x over here. Because if u was just x, you wouldn't be able to get rid of the natural log of x. Yeah. I see what you mean, though. That kind of looks, I see. Example 5, integral of x squared e to the x cubed dx. Okay, so I have u, let u be x to the 3rd, so just that exponent on the e. And then what would du be? Yep, 3x squared dx. So we have the x squared, we have the dx. We don't have the 3. So divide by the 3. 1/3 du would equal x squared dx. The exponent is now u. We have 1/3 du for the x squared and the dx. And the 1/3 we can write in front. So 1/3 times the integral of e to the u du. So the 1/3 stays. Antiderivative of e to the u is e to the u plus c. Put u back in. 1/3 e to the x cubed plus c. In some cases, as long as you realize that finding any integral is finding the antiderivative, I'm just thinking, I'll say this again, but sometimes when you look at a function, even like number 8, even if substitution rules should be used, sometimes you can just kind of reason through or picture what the antiderivative would be. Like what function gives you that as a derivative. I'm going to have you be doing 7 and 8 together. I do want to go through 6 with you, though. That would be the derivative of tangent. So, yes, this is asking the integral of tangent of x, meaning tangent would be the derivative of something. So, of the trig functions we have, none of them have a derivative of tangent. Cotangent squared, yeah. So right now, as this is, I can't say, okay, u is tangent of x, because then du would have to be secant squared. I don't have a secant squared. Okay. I can rewrite tangent as sine of x over cosine of x dx. The question is, which do I choose for u? Okay, so if I choose u as sine of x, what would du have to be? Now, hold on a minute. If I rewrite this, this is the integral of, this is really sine of x times, and since cosine of x is in the bottom, it's 1 over cosine of x. So if I let u be sine of x, I don't have cosine of x dx. I have 1 over cosine of x dx, which is really secant of x dx. This doesn't work. Okay? All that means is I would choose the other one. If I choose cosine, because if I have 1 over u, that's fine. So if I have u is cosine of x, du then, the derivative is negative sine of x dx. But then my cosine of x, I now have 1 over u. I do have sine of x dx, I just don't have the negative. So that means it would be negative du is equal to positive sine of x dx. So the negative would have to go in the integral. Okay, so double check. That's how you know if something works or not, is it going to be replaced exactly the way I'm writing it? If I choose, in this particular integral, if I chose u as sine of x, it would not work. So now this integral becomes, I need the negative in there, and it's the integral of 1 over u, and then sine of x dx becomes the du with the negative in front. So I have negative, what's the antiderivative of 1 over u? Yeah, natural log of the absolute value of u. Okay, so negative natural log of the absolute value of cosine of x plus c. Yes, so this is the antiderivative of tangent. You don't have to memorize it. If you really want to, you could. Maybe. All right, 7 and 8 I'd like you to try. So find those two integrals, find their antiderivatives. Number 8 does involve a substitution. However, you might be able to just reason what the antinatal should be.
You just said it. You have negative 1.5. Because I never changed my answer. I see all your original. Oh, I thought you had one pound.
Yeah, so it's kind of like it marks the end of the integral, but the integral symbol and the action where there is a here's my Right, so you divide by it. If I didn't already check your answers and you want to make sure they're right, some of you had 7, you weren't done with 8 though. So
We finally got it.
practice is there. Let me know tomorrow if you have questions.